Example 7. Find the magnitude of the equilibrium of forces 54 newtons and 42 newtons acting on a point A if the angle between the forces is 98 degrees. Then find the angle between the equilibrium and the 42 Newton force. We need to round everything to the nearest whole number. All right, let's start by drawing this out. So we have a point A, and point A is being acted upon by two forces that are separated by 98 degrees. Okay, so I'm going to draw a 98-degree angle here, or approximately a 98-degree angle. So this is going to be one of the forces, and this is going to be the other force. Okay, so this is a 98-degree angle. Let's say this is the 54 Newton force and this one is the 42 Newton force. Okay, so this is kind of an illustration of what's going on, and we want to find the magnitude of the equilibrium. Okay, so here is that word. We saw it in the box above, but we really haven't worked with it yet. So let's go back up to the top here and review what this means. Okay, it says sometimes it is necessary to find a vector that will counterbalance the resultant. This opposite vector is the equilibrium. That is, the equilibrium of vector u is the vector negative u. So what's going to happen here to find the equilibrium? We first need to find the resultant. And then once we have the resultant, the equilibrium is the opposite vector of the resultant. Okay, so let's concentrate on the resultant, and then once we have it, we can talk about the equilibrium. Okay, so remember the word resultant. That means to add the vectors. Okay, for this particular situation, how we can think about the resultant vector, say point A is a rock, and then you have these two forces that simultaneously act on the rock. So the resultant vector is going to show us where the rock ends up. Okay, so that's how you want to think about it. Okay, so again, we're going forward, concentrating on the resultant, and then we'll deal with the equilibrium. Okay, so we need to add the vectors. That's the definition of resultant. So you've got the two different methods for adding your vectors. We have it already set up where our two vectors share the same initial point. So it's best to use the parallelogram method here. So I'm going to come in and draw a parallelogram. So this is going to be the side that is parallel to the 54 Newton force. And then we'll say that this is the side parallel to the 42 Newton force. Okay, so here is my parallelogram. And so we know that to draw in the resultant vector, we're going to start at the point where the two vectors coincide, and we're going to draw the diagonal across. And so this red vector is the resultant vector. Okay, so this is the resultant. Okay, so you can think of it, like I said, if you thought of point A as a rock and these two forces came in and acted on the rock is going to end up right here at the end of the day. Okay, so the directions say to find the magnitude of the equilibrium. I am going to go ahead before I go into the equilibrium. I'm going to find the magnitude of the resultant. Okay, and then, like I said, we'll talk about the equilibrium. Okay, so we've got a parallelogram here. So I know that this side has to equal this side. So this side has a magnitude of 42. This side has to equal this side. So this is 54. Okay, and we can figure out these angles right here because this is a parallelogram. I can figure out the measure of this angle and this angle. In a parallelogram, the angles have to add up to 360, and we know that this angle right here is 98 degrees, which means this angle is 98 degrees. Okay, so if we take 360 and subtract both 98-degree angles, that is going to leave us with, let's see here, that's going to give us, we have 360 minus 98 minus 98. That's going to leave us with 164 degrees to split between the two remaining angles, and they have to be equal, so we need to divide by 2. And so see, each of these green angles is going to measure 82 degrees. Okay, so that's going to be the measure here, and then that's the same as the measure here. Okay, so like I said, we're trying to find the magnitude of this red vector. Okay, so I'm going to shade in one of the triangles here, even though they're the same. Okay, let's look at this triangle. Look what I know. I know a side, an angle, and a side. So this is a SAS case, and I can use the law of cosines to figure out the length of the resultant, or the magnitude of the resultant. Okay, so let me jot this down. This is a SAS case. We're going to use the law of cosines. Okay, let me put some vertices on here. We're already calling this point A. Okay, this 98-degree angle is angle A. Okay, or actually, hold on. When this is point A, okay, this angle right here is 98 degrees. Okay, if we're looking at this triangle, okay, this would be angle A in the triangle. Okay, so actually, to avoid some confusion here, let me put on different letters here. Okay, so I am concentrating on the yellow triangle. Okay, I am going to label this, let's see, let's do X, Y, and Z. Okay, so let's say for this yellow triangle, this is point X, this is point Y, and this is point Z. Okay, so that way this is angle X, this is angle Y, and this is angle Z. So there's no confusion between the angles inside the yellow triangle and the 98-degree angles. Okay, so if we go across from angle Y, that is the side we're looking for. So we're looking for lowercase y. If we go across from angle Z, 54 is going to be Z. And if we go across from X, okay, this is going to be side X is the 42 here. Okay, so we are trying to solve for Y. Okay, so if we apply the law of cosines here, we need to solve for y squared. Okay, so this is going to be x squared plus z squared minus 2 times x times z times the cosine of angle y. Okay, so let's pop all of this in. So to get y squared, this is going to be x squared, that's going to be 42 squared plus z squared. Okay, so z measures 54. So 54 squared minus 2 times 42 times 54 times the cosine of angle y. Angle y is 82 degrees. Okay, this is going to give us the value of y squared. So let's put this in the calculator. We're going to get 42 squared plus 54 squared minus 2 times 42 times 54 times the cosine of 82. Make sure you're in degrees. Okay, so here comes the answer. So this is going to be 4,048.710814. Okay, 710814. Okay, we want the value of y, so we're going to have to take the square root. Okay, don't worry about the plus or minus because we're finding a distance, and so we just need to go with the positive version here. Okay, because we're looking at magnitude, not direction. Okay, so this is going to be 63.6294807. Okay, and that is the magnitude of the resultant force. Okay, if you go to the directions, it says to the round to the nearest whole number. Okay, so I'll go ahead and do that here. Okay, so after the decimal point, there's a 6, so I'm going to bump this up to 64. Okay, this is a force. It is the resultant force, so this will also be measured in newtons. Okay, so this is not the answer because this is just the magnitude of the resultant force, but we need the magnitude of the equilibrium. Okay, so I'm going to draw the equilibrium in. Okay, it is basically the opposite vector of the resultant. Okay, so I'm going to align myself with the resultant. So I need the same size, but I need to go exactly in the opposite direction. Okay, so that the resultant and the equilibrium form a 180-degree angle. Okay, so this, just eyeballing it, this vector on this side is the equilibrium. Okay, so the thing to realize, okay, these two offset each other. Okay, they counterbalance. They're counterbalancing forces. Okay, they have the same magnitude, just opposite direction. So since they have the same direction, and I'll write this here, the resultant and the equilibrium have the same magnitude, but opposite directions. Okay, we're asked for the magnitude of the equilibrium, so that means it's going to be the same as the magnitude of the resultant. So this actually is what we're looking for. Okay, so I'm going to write right here, this is the magnitude of both the resultant and equilibrium forces. Okay, so that's the first part of the question. Okay, we had to find the magnitude of the equilibrium. There's a second part to the question. Now we need to find the angle between the equilibrium vector and the 42 Newton force. Okay, so going back to the picture here, let me try to mark this in a different color. I'll choose pink. So that is going to be this angle right here, the angle between the 42 Newton force and the equilibrium. Okay, so I'll call this theta. This is what we're looking for at this point. Okay, we need to figure out the measure of this angle. Okay, so here we go. When we look at this, okay, remember this angle in blue is 98 degrees. Okay, what we can do is shift our focus to this triangle, which is equivalent to the yellow one. Okay, but I'm just going to look at it instead because it's on the same side as this pink angle. And what do we know about this green triangle? Well, we know two of the sides and we know one of the angles. Okay, because when I shade this in, I know this side is 42, this angle is 82, and this side is 54. Okay, so what I can do here is this is a SAS case, okay, just like the yellow triangle. We can use the law of cosines here to figure out this angle, and I need another color. I'm running out of colors. I need to figure out this angle right here, this purple angle. Okay, we need to figure out what that angle is. Okay, and it disappeared on me. If we can figure out what this purple angle is, I'll call it, I don't know if I'm going to name it just yet, but if we know this purple angle, we can add, if you add the purple angle to theta, that should be a straight line. So that sum should be 180 degrees. So we need to use the law of cosines, because this is a SAS case, to figure out the measure of this angle. Okay, so here we go again. Okay, I need to put a coordinate system on here. I already have called things, this is point X, this is point Z. Okay, this is going to be point, I'll do something else. I don't know, let's say W. Okay, so this is going to be point W. I am trying to compute what? Well, if this is going to be angle X. Okay, so I'm trying to compute angle X. It is getting very congested in here. Let's see if I can remove some of this congestion. Hang on. Okay, so let me shade this. Let me shade this. Okay, so right now I am trying to figure out this angle, which is angle X. Okay, if I go across from angle X, side X is going to be 54. This is going to be angle Z right here. Okay, if I go across from angle Z, Z is going to be 42. Okay, and then we know W is the same thing as Y. Okay, so W is that 63.62 blah 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 number. Okay, all right, so we are applying the law of cosines here to figure out angle X. Okay, remember I'm not using A here because angle A as a whole was that 98 degree angle. Okay, so I'm trying to avoid confusion with that. Okay, so if I set up the law of cosines to figure out the value of angle x, I'm just going to jump to a new page here because I'm running out of room. Okay, this is going to be x squared is equal to, let's see, oh, wait, I didn't use y here, I used w. So w squared plus z squared minus 2 times w times z times the cosine of angle x. Okay, we want angle x, so we need to solve for this guy. Okay, so if I move the w squared over and the z squared over, this is going to be x squared minus w squared minus z squared is equal to negative 2 times w times the cosine, wait, is equal to negative 2 times w times z times the cosine of x. To isolate the cosine of x, I need to divide both sides by this quantity, and now I can plug into it. Okay, if I want the cosine of x, this is going to be x squared minus w squared minus z squared all over negative 2 times w times z. Okay, so let's plug in here. The cosine of angle x is going to be x squared. Okay, so x is 54, so this is going to be 54 squared minus w squared. Remember, w is the same thing as y. We have to use the full decimal approximation here. So this is going to be that 63.629 number. You have to, for accuracy, use the full thing. Whoops. Okay, and then you have to subtract out z squared. Okay, z in this case for the green triangle is going to be 42 squared. We're dividing this by negative 2 times w, which is that decimal, times z, which is 42. Okay, so let's go to our calculator and plug this in. Okay, so here is that lovely decimal. I am going to store this in w. Okay, so that I don't have to keep punching it in. Okay, so here we go. I'm going to type in the numerator. So it's going to be 54 squared minus w squared minus z squared, which is going to be the 42 squared. So this is the numerator. We need to divide this by negative 2, and make sure you put the entire denominator in parentheses. Negative 2 times w times z, which is 42. So this is the cosine of x. Okay, so I'm going to go ahead and jot this down. So this is going to be 0.54196030 16. Okay, we need the full decimal expansion here. This is the cosine of x. And so now if we want just x, we need to take the cosine inverse of both sides. Okay, so just write this out. All right, on the left side, cosine inverse and cosine cancel. That's going to give us the value of angle x. Okay, so let's do the cosine inverse of this quantity. Okay, here it is, 57.18 281497. This is measured in degrees because our calculator is in degrees. Okay, so if we go back to the problem, that is angle x. Okay, what we know is that we're trying to find theta. Theta plus angle x, that sum forms a right angle, which is 180 degrees. So to get theta here, we need to take 180 degrees and subtract the value of angle x. Okay, so let's do that. Okay, so I'm going to get theta is equal to 180 degrees minus angle x. Okay, so that's going to be 180 degrees minus this decimal that I just got. Okay, and let's do that. So I'm going to take 180 and subtract out this result. Okay, and then there is my number. Okay, so we were told, I'll go ahead and jot this down, but I think we were told to round to the nearest whole number. Okay, so theta is going to be 122. Let's see, 817 185. Okay, so we can round this to the nearest whole number. So since there's an 8 after the decimal, we need to bump this up to 123 degrees. Okay, that is the value of the angle between the 42 Newton force and the equilibrant.